Now this is circular motion. It's starting with a few bits of notation. We'll denote ds by dt as s dot and d squared theta of dt squared as theta double dot. Now the figure above shows a particle P moving around the circumference of a circle of radius r and its centre O. At a time t, the position vector is OP. Vector OP. A rough particle makes an angle of theta in radians with a fixed direction OA, and the arc length P is denoted S, which is here. Now we're forming the angular speed, we have S equals r theta, and differentiating with respect to time using the product rule, it gives us this, where since r is a constant, we get dr by dt equals 0, so the rate at which the arc length increases is given here. Now here S dot is the speed at which P is moving around a circle, and theta dot is the rate at which the angle is increasing, rate at which the position OP is rotating. Now theta dot is the angular speed of P. Now it's positive when theta is increasing, that means anti-clockwise, and negative when decreasing clockwise. Now the angular speed is often written as this, which you should be a little bit more familiar with as an omega term. So S dot equals R, theta dot is equal to this, V equals R, R omega. Now here's an example. A police car drives at 40 miles per hour around a roundabout in a circle of radius 16 meters. A second car moves so that it has the same angular speed as the police car, but in a circle of radius 12 meters. Is the second car breaking the 30 mile per hour speed limit? Well, we use the approximation here. 1 mile equals 8/5 of a kilometer. Now the solution, 40 miles per hour equals 40 multiplied by 8 over 5 kilometers per hour. So we're converting this into meters per second, which is 160 over 9 meters per second, using V equals R omega will give us the omega after dividing through. We get 160 over 9 multiplied by 16 in radians, which is 10/9 in radians. So the speed of the second car equals 10/9 multiplied by 12 meters per second, or converting this into miles per hour is 30 miles per hour. So it's dead on the speed limit. So the second car is moving at the speed limit. Now velocity and acceleration. For a particle moving around a circle of radius r, the velocity has a radial component and a transverse component, r theta dot or r omega. Now the acceleration of a particle moving around a circle of radius r has a radial component negative r theta double dot squared, or r minus r omega squared. Now the transverse components are written as this or this. So we'll often use this kind of notation, this is easier. So shown pictorially in these two graphs is here. Now the transverse component is just a radius multiplied by its angular acceleration, theta double dot. If the particle has a constant angular speed, its angular acceleration is 0. So transverse component of acceleration is also 0. In contrast, the radial component of acceleration, negative r omega squared, tells us that a particle that's travelling in a circle is always accelerating towards the centre. Now here's a derivation of some of the expressions. When a particle moves in a circle, it is convenient for the velocity and acceleration to be expressed in radial and transverse, i.e. longitudinal directions. So the unit vectors are r dot and theta dot are defined in these two directions. The vectors are not constant. They change in direction as the particle moves around the circle, which is given here. And this shows r hat and theta hat, where when particle P is at a general position. Now you can see here, given in general polar coordinates, r hat equals cosine theta I plus sine theta j, and likewise for theta I equals negative sine theta I plus cosine theta j. And differentiating r hat with respect to time, we get this here, which equals this, where theta dot equals d theta by dt. Note a vector in brackets is the same as theta hat, the unit vector in the transverse direction. Consequently, we get this, and similarly we get this. So these two vectors, d r hat dt equals theta dot theta hat, and d theta hat t equals minus theta dot r hat. Now these apply to all motion in polar coordinates, not just circular motion. In the case of circular motion, the radius r, displacement from the centre at any time is r hat. And now differentiating with respect to time, we'll find the velocity, which is given down here, where r is constant, which in this expression here, which gives it in its transverse direction. So if we take this, we differentiate again, we'll get this equation here. Now the acceleration has two components, the transverse and the radial component. Circular motion with constant, and so now we get on circular motion with constant speed. Circular motion assumed uniform and has no transverse component of acceleration. So the problems involving circular motion often refer to angular speed of the object rather than its angular speed. To convert one to the other, we use v equals r omega. This can also be used to express magnitude and acceleration in terms of v and r. Now omega, as we already established, is v over r. So the acceleration is r omega squared. So we plug in the value for omega squared here, which is v over r squared. So the acceleration is given here, and it's acting, like we said before, towards the centre. Now here's an example. A fly standing on a record at a distance of 8 centimeters from the centre. Now if the record rotates at a speed of 45 rpm, we find 1, the angular speed of the fly in radians per second, 2, the speed of fly in meters per second, and 3, acceleration of the fly. Now the solution of the first one, 1 revolution is 2 pi radians, so 45 rpm equals 45 multiplied by 2 pi radians per minute. So we're plugging in these values and we'll get 3 pi over 2 radians per second. Now the speed is, we're simply plugging in values for all of these, which is v r omega. So we get 0.38 meters per second. The acceleration r omega squared. So again, we're plugging in these values and we get this value of 1.78 meters per second squared. And it is again directed towards the centre. Thanks for watching, and please do subscribe.